Thank you so much, David. And it's definitely a distinct pleasure to be speaking in this seminar series. As David correctly mentioned, he and I have distinct pleasure of being the co-fathers of this seminar series long ago when it was a tiny. And this is my first time speaking in this, so I hope it's not last. All right, so with that, I'm going to talk about causal matrix completion. This is based on joint work with Anish Agrawal, who is sitting in red mask there, Mnr Setting, who is in beautiful peacock mask there, and Danish Sen, who is a former student here. When he was a student here / postdoc, this work started, and now he's a postdoc at Berkeley with as a part of FORTC with Bin, Peng, and Jess. This is the manuscript that got uploaded yesterday night. So if you find typos and errors, please do send them, be kind. This is another associated paper that is kind of a precursor. So in case you're not bored with all of that, you would go there. All right, so with that, let me get started. This is the outline for the talk. I want to just quickly remind us what the problem of matrix completion is. Looking at the audience, many of you have deeply contributed to the field. So, but at the same time, if you have not seen this before, I'll spend a few minutes. Hopefully, I'll amuse you with few interesting applications of matrix completion that you might not have seen before. After the question and examples, I'll go to the model. And again, like any estimation or signal processing problem, we want to know what the signal structure is. We'll talk about the signal structure and something about observations. And observation is the key. That is what we observe and what we not observe. There is a causality there, and that's going to sort of form the basis for this talk. I'll do very brief literature review, and again, it's going to be super brief because the literature is so large that it's impossible to cover. I'll briefly describe a few of the algorithms and quickly some of the results, and in particular go to the dimension in which I want to focus on, and that will pave a path towards the contribution of this work, which is the algorithm and some of the results. And finally, I would like to spend some time doing discussion where I think that matrix completion as a topic is an interesting way to at least try to address some of the causal inference problems, some of the causal inference problems with observational data. And maybe I'll spend time discussing that through a caricature, but hopefully caricature will be useful to understand why some of these things might be useful. All right, so with that, let's get started with the question of matrix completion. Again, it's a super simple and super clean question. The way it goes is as follows. You got a matrix, m rows and columns. And here I'm showing you 5 columns and 5 rows. Okay? And some of the entries you observe, some of the entries you don't. Okay? The idea is that the entries that you observe are noisy version of the true underlying entries that you care about. And entries that you don't observe, of course, you don't observe. Okay? So one way to think about it is, let's say these are the outcomes of potentially 25 coin flips. So I've got 5 rows and 5 columns. Each entry corresponds to a coin with its own bias. Okay? And for some of them I observe head, some of them I observe tail, and for many of them I observe nothing. Okay, and if I told you to estimate bias of all coins and I didn't tell you anything else, you'll say, well, that's a ridiculous problem. So clearly you need some structure in the matrix and all that, and that's roughly what matrix estimation is all about. And that's also one of the reasons why I believe that it's a great way to look at this high dimensional modern statistics problem, right? And that's also the reason why it has driven a lot of that progress over years now, at least 2 decades. Okay, so that's the question, formalizing a little bit more, and I'll sort of add more and more model as I go along. First, I'll just add the formalism, no probabilistic models yet. So this is my ground truth matrix. I observe entries of partially observe some of the entries, and whenever I observe something, hopefully it has something to do with underlying ground truth, and we'll discuss that a little bit more. Whatever these observations are, that is why matrix is. From there, I want to estimate A hat, which is hopefully a good approximation of A. Okay, and what do you mean by good approximation? Well, you can sort of come up with all sorts of matrix norms of your interest. It could be, future I should keep it a little high. Maybe operator norm, maybe to infinity norm, that is squared error across, maximum squared error across column or rows, or for every entry I want to sort of keep error small, and so on. Okay. All right, so that's the task. Now, before I go into the former model, I'll give you, as I promised, few interesting examples. These are some of the examples that I have personally spent time thinking about, and hence I like them. Of course, they're not all of them. So here's one example. So there's a classical model called multinomial Logit model. The oldest reference is 1926 work by Thurston with an E. And then sort of McFadden sort of used it heavily in the world of econometrics. Looking at one way, it's a distribution over permutations. Okay, so you got n elements, okay, n players. Each player has some skill called Wi. Okay, and now I want to produce a distribution over these permutations using these parameters. The way I would do that is, well, first position goes to the element with element I, where I'm sampling I with probability proportional to Wi. Then remaining n minus 1, I will do the same process and so on. With respect to this model, effectively what happens if I ask question, what is the likelihood is that I is going to go into higher position than j? That likelihood is exactly Wj over Wi plus Wj. And because this only depends, this pairwise ordering only depends on I and j only and nothing else. For that reason, it's also satisfies what's called Lewis' axiom, and then this becomes kind of a unique solution of Lewis' axiom that came out in 1946 or something. Anyways, that's a bit of a history, but here, let's say my matrix that I'm interested in is precisely Aij that I want to estimate. Okay, that is Aij is what is the likelihood that j defeats I, okay, or j is likely to be ranked higher in my distribution. And what I will show you is for some ij's, either pairwise comparison or nothing. Okay, so only a small fraction of pairs of players play. Of course, the way whole thing is set up, expectation of Yij is going to be Aij. Okay, and now I want to learn A from these pairwise things, and basic calculation will reveal that if you estimate A well in the operator norm with a little bit of work, then actually you will be able to estimate W as well too. Okay, so this means that here is one type of norm you want to estimate that gives you good estimation of the parameters that you care about. Okay, and this is a matrix estimation problem. Okay.
So but the statement that the difference in the operator norm is small seems fairly strong, right? So you would have to not only see all of the pairs like once, you would probably have to see them a bunch of times.
Good. So yeah, so there's a little bit more work that one will have to do to go from actually to do this translation, and that's why there is a iterative denoising algorithm.
Okay.
But this is one of the key steps towards that. Okay. Great. Yes.
So you only learn W up to a constant?
In this statement, you will get good error in W in the normalized 2 norm. So it's W hat minus W divided by W's 2 norm.
But don't we only technically know Wj over Wi plus Wj? So like that's our assumption.
So you'll have to do a little bit of work. That's here. Okay. Yeah.
So in this setup, you directly estimate A's or W's?
First, from Y's, I'm going to go to A's.
So you estimate A under what structure?
Under exactly, okay, good. So what are the observations from in terms of what entries I have observed, right? This is where I'm observing some entries, but whenever I'm observing an entry, I'm observing independently of everything else. Okay, and the structure of that observation would form some kind of, let's say, graph adjacency matrix. The Laplacian of that would determine error here. Great question. Sorry, I'm glossing over that.
That's fine.
Thank you. Okay, great. Okay, so here is a place where the to infinity norm error becomes very useful. So let's say I've got a time series, there's some underlying time series f1, f2, ft. These are noisy version of that with lots of them missing. Okay, what I'll do is I'll convert that into its page matrix. Sorry for this typo. So x1, x2, xl. So I'll take first L entries, make it a column. Next L entries, make it another column. Next L entries, make it another column, and so on. So just like the typical Hankel matrix subsampled to avoid dependencies in the entries effectively. This will be a noisy matrix with lots of missing values. Assume time series has all the missing observations. So if underlying time series had a nice structure, then this would become a nice instance of a matrix estimation problem. And if I estimate this matrix well with respect to error of to infinity norm, then I could convert it into a reasonable forecasting method. Okay. All right, and this also in the literature, this type of method would be known as the singular spectrum analysis method. Okay. All right, and I mean, this is great, but I think this the really nice thing is resulting algorithm is super simple. So if you want to run it in real time, where let's say time series data is coming in and you want to constantly update your model, incrementally update it and make predictions, actually it works well. And there's a nice system that we've built, primarily project led by Abdullah Alomar. I don't know if he's here behind mask, but we put it out there here as an open source. Please feel free to play with it, give us feedback. Really appreciate it. There's a nice demo that Abdullah did last NeurIPS showing how the system works. So there's a nice sort of documentation around there. Okay. And the last one that, or second last one that I'll show you is this: what if you can estimate a matrix really well with respect to infinity norm under a little bit stringent constraint. So my ground truth matrix is Aij, where I corresponds to state and J corresponds to action in a generic MDP setting. Okay, so I've got a Markov decision process, the typical framework for reinforcement learning. Aij corresponds to true underlying Q function. So I'm not defining it. If you know what Q function is, you know what Q function is. If not, my apologies. Okay, so Aij is the value of Q function at state I for action J. That's how I'm thinking of it. And let's imagine that I have noisy observations of Aij, which is Yij for some of them, where I know it's bounded by some deterministically by some delta. I don't know what the error is, but I know it's bounded.
So Q
Yeah.
is, I don't know, Q is the right?
No, sorry, good, thank you. So in the typical MDP, right, the model would be that you have some dynamics, and the dynamics is driven by underlying system dynamics and the action you take.
Yes.
So you have a state at time t+1 is determined by what action you take at time t and what state you take. And the Q function associated with the given state for any action would effectively tell you that if you took this action A for a given state at this time, in some sense the long-term reward that you care about under best policy subsequently, assuming you are going to take the best actions afterwards, it would look something like this.
So it's a reward function.
It's a reward function under the best possible policy starting now for long term.
With the time discounted or steady state?
Good. So now, okay, so think of infinite horizon setting, think of discounting, then the reward would be rewarded this time, rewarded next time times the discount factor, reward next time. That's it. Good. Perfect. And Q function is effectively that mysterious object. Say hypothetically I gave you Q function, then it's great because you as running an RL system, you will say at this state, for every possible action, I'm going to ask what is a Q. And the A with the highest Q, I'm going to take action and I'm done. So that's why say one way to think about this is the mother. If I know I'm done, answers are there. So let's try to estimate it. Well, if you have a simulator for underlying MDP, model simulator, let's say there's a way to generate a noisy observations for this matrix that have properties like this. Okay. So if from these kind of observations for limited entries for the matrix, if you could produce an estimator like this, that is good estimator for all entries with maybe a little bit of blow up in error, then that would actually lead to a really nice statistical improvement in terms of performance. Okay, that is, you don't really need to do lots of simulation, you need to do exponentially less simulations. Okay, yeah.
So for a lot of these, I mean, your ability to complete matrices and different norms depends on some sort of underlying structure.
Absolutely.
In the matrix. Right?
Absolutely.
So for the first problem, for the multinomial, there
Logit.
the structure came through the W's, right?
That's correct.
So for the last two examples, I mean, is it clear what structural properties, let's say, about an MDP?
Yeah.
Are there things that imply that the Q function would
Has a nice structure. So for example, let's take one traditional benchmark from classical systems theory you would take is LQR. Okay. For that, Q function is a finite rank. Okay. More generally, if you have a reasonable sort of
wait, what? I mean, okay, so it's a finite state space, LQR? I mean,
no, it's continuous state space, continuous action. Okay. But sort of the underlying Q function defined on that would as a function decomposition. So let's say if you Q of S comma A, you wrote it as f of S G of A, yeah, and sort of finite number of such terms that will add up. In that sense, it's a finite rank. So if you subsample the states and actions from that function, then sort of the resulting matrix will be finite rank.
And the finite bound would come from the linear dynamical system underneath the LQR?
No, actually, for Q function, it has a nice property for that. Okay. There was a nice paper in 1990 something that sort of actually laid it out. More generally, if you have, let's say, nice transition kernel and a nice reward function, let's say Lipschitz, then this will be well approximated by approximately low rank, and that would lead to this kind of things. So there's some such conditions we've identified in this work. Thanks. Yes, so I'm doing a lot of black box here, so I apologize for that. But I thought, typically one thinks of matrix completion as a Netflix problem from 2006, and that's actually a gimmick, as he's laughing. But I feel it's not just a gimmick; it's a great black box to solve lots of harder problems, and that was my hope. All right, and the last one, that matrix completion with various norms, and in a sense, starting point for this work was for a setting of what panel data is. All right, let me sort of skip this because I feel I'm spending a lot more time than I wanted to on this part. Okay, but bottom line is that sort of different norms would lead to different causal estimates, and hopefully it will make sense by the end of the talk. Okay, so let's start with the typical model in the matrix completion literature. To do this kind of good estimation is you have to assume some structure. So one type of structure would be that, well, underlying ground truth is some latent function of latent features associated with rows or factors and latent factors associated with columns. And maybe these factors are coming from nice space, that's a 0, 1, just one dimensional interval, or d dimensional interval where d is small. Okay. And of course, low rank is an instance of this. And throughout this talk, I'm going to assume it's low rank. Okay. And R is small. Okay, it doesn't scale with the dimension of matrix. Okay. Now, what about factors? Are the factors arbitrary? Do they have some structure? So there are, again, two schools here. One school would say that these factors are sampled, like a Bayesian-like view, from distributions. Another school would say, well, forget about that. I'm just going to assume certain conditions about given factors. And I would say there's an incoherence. Like effectively, it avoids terrible scenarios like you have a matrix with all interesting things happening one entry and everything else is not, and really your error would be driven by your lack of ability to capture information about that one entry. Okay. And there's a really nice work, again there is lots of nice work in econometrics literature, and more recently a paper like this. For example, it tries to argue that some of these properties are very closely related to each other. They are not very different. Okay, but there is lots of interesting questions that are there. Sort of some of them I don't know how to answer, and I'll at least ask few people. I think it will be interesting to sort of answer some of them. Because if you assume these kind of conditions, you get certain type of result. If you assume this kind of condition, you get certain other type of result. So it will be useful to resolve similarities and differences there. The other part, so there was a structure in the signal, that is what the underlying matrix has. Now let's talk about the observations. How are observations there? Well, if you observe an entry, let's assume there is an additive noise. The additive noise's distribution might depend on the entry. For example, let's suppose Aij is a number between 0 and 1. It's a bias of a coin. Okay? So I'm going to observe 1 or 0. So of course its distribution depends on the actual Aij, but it's independent and it's nice, right? It's in this case it's bounded noise, or more generally I'll assume that it is a sub-Gaussian. The next question comes is, okay, so which entries do you observe? How do you decide which entries you should observe? And this is where the crux of the talk comes. Typically, at least it started out by looking at the question of missing completely at a random, or MCAR. Okay? Where the idea would be that every ij, you flip a coin independently with bias p. If it comes up head, you observe. If it comes up tail, you don't observe. Okay? And then there's, of course, everything that's not MCAR is Mnr, missing not at random. And I'll sort of open brackets here in a second, but this is nicely sort of discussed in these two references, and again goes back to some of the works that Rubin and colleagues started a while ago. Okay, so for Mnr, of course, there's lots of different ways you cannot be MCAR, right? I mean, completely at random is one thing. Anything that's not completely at random is Mnr. So there are lots of different things. In particular, it can be terrible. Okay, so one needs sort of different layers of models there. One layer of model that has been very popularly studied over past 5 or so years is called limited Mnr. Okay, this is the term I'm introducing to keep the conversation simple, because the notations, there's a definition called MAR in the literature as well that I think would be attributed to Rubin, right, Raz?
Yes.
Yes, and that's a little complicated. Okay, that's all I would say here. So I'm going to call this intermediate model called limited Mnr, and then I will call causal Mnr that I will introduce. Okay, so what is this? Here the idea is that each entry, again, is observed independently, but the bias of the coin is different. And this bias of the coin, of course, if it could be arbitrary, again, we are in trouble, because if there's no structure, the few conditions you would require, one is what's called typical in causal inference as positivity. If you look at Imbens and Rubin, what it says is, even in this case transported, it will say that the minimum probability of observing something is lower bounded by some p star. Okay? And there is a structure in P. For example, Pij itself is satisfying a latent factor model. But moment this happens, it kind of gives you a nice simple result that sort of, I would say this at the end of my talk in 2017, and I thought, who would write a paper about it? But here is sort of what you can do. Well, now you got two models, right? First, you take your observations, remove the actual values, just observe the mask, okay, and apply your matrix estimation procedure on that, because now you're getting effectively MCAR, right? Because it's P star times something, and times something is what you're trying to estimate. So you will estimate the mask first. Once you have estimated the mask, you go and actually estimate the entire matrix as if you observed everything. There's no missingness there. And then take the sort of the entry-wise division of what you estimated divided by the Pij, or your estimation. And there will be a reasonable estimation of that, yes?
So in this model, I mean, would you be okay, you know, things would be fine if everything were just observed independently with probability P star to this, or?
So everything is, so Pij, so every ij is observed with probability Pij.
Right, right. But if you considered like, you know, the restricted form of the model where all of the Pij's weren't heterogeneous and they were all P star,
Then it will
things
be,
would be okay and you'd be back in the original model.
then this will be my MCAR.
So I guess what I'm confused at is like, you know, so actually, I mean, I think there's another way that this model is studied is sometimes it's called like semi-random matrix completion.
Okay.
Because imagine you observe entries uniformly at, you know, P star bias for all the entries,
Mm-hmm.
but then an adversary comes along and reveals more entries.
Okay, sure,
So that, you know, can certainly contain this issue of, you know,
sure.
Pij.
Mm-hmm.
But don't all of the semi-definite programming things just work off the shelf for these things, or?
Well, I mean, all I'm saying is that you can divide this into two MCAR problems. So semi-definite programming things would work for MCAR things.
Scaling up the semi-definite program is going to be a nightmare.
No. Because it just adds.
No,
more
he's talking about sort of the, at least
it
the
just
statistical
adds more
part.
constraints.
Okay.
So it's exactly the same thing. You don't actually need the structure assumption.
Let me sort of not answer the question about answer that question because I've not fully thought about that. But all I would say is that this model would be two MCAR models, and since semi-definite programming approach works for MCAR models, you're going to just apply it twice and use the union bound. Okay, and it'll be just fine. Now, there's a sort of nice variations that sort of many of these things are proposed of this style of method. There is more than just what I'm saying, like trying to bring the typical causal inference approach, like inverse propensity weighting, along with appropriate loss function and so on and so forth. But that's roughly what's happening in these really nice works.
But this is not adversarial model, right? In
Yeah.
adversarial model, I assume that you first reveal some entry and then adversary, knowing what you have seen, adds some additional things. So this, in your model, Pij would be dependent on what you see in the first round, if I understand it correctly. Here, Pijs are nominally already preset a priori and just heterogeneous probabilities.
Right, but I guess what I'm saying is that some off-the-shelf algorithms tolerate the heterogeneity for free.
Right.
Because
Okay.
for something like an SDP, you know, if you bake it in as everything gets observed uniformly with the probability P star,
Mm-hmm.
and then something happens afterwards, those end up being more constraints on the SDP. So when you pass the dual to sort of show that the optimal thing is, you know, the right answer, like the Planta thing, those proofs still work, right?
So, but again,
That would
so.
be something, probably.
But again, sort of to get to the A's,
Yeah.
so what will end up happening is likely that you will end up estimating P times A's entry wise rather than just A's. So you will have to sort of do correct for P's one way or the other. Okay. All right. So what's the model we're going to talk about? Here's the model. I'll call it a causal model, and I'll explain it in a second why I'll call it causal model. So let's say Dij's are random variables representing whether entry ij is revealed or not, 1 or 0. Okay, they may be dependent. It's a generic function of the underlying latent factors, and remember I've got a rank R setting. So aij is ui transpose vj. Okay. I will require conditional independence of d from y. Particular look at the DAG. So latent factors. So y is latent factors plus epsilon. Okay, and so y is determined by these two. Latent factors may sort of determine the distribution of epsilons. Okay, latent factors may determine d arbitrarily. However, I will prevent this chain, that is idiosyncratic noise cannot determine my decision of which entries I'm going to reveal or not. Okay? The characteristics of the entry through the latent factors can determine which entries I'm going to reveal or not. Okay, so for example, if I know that this row I is a very pleasant users who give good ratings to everyone in general, that might determine my decision of whether I'm going to reveal that or not. But then once I decide whether an entry is revealed or not, the noise that I add to that is not sort of accounted by this. Okay, and that's the only restriction. Because if I added that restriction, it will become everything. Okay, this in the causal inference, it allows for confounding because D and Y are not independent, and I'm okay with sort of having lack of positivity. Okay, I have to put some constraint under what condition under this I can still sort of recover something, and that sort of we'll discuss in a second.
Just to understand
Yeah.
the model. So U and V are one-dimensional.
So let's say U and V are r-dimensional. So the matrix is rank R matrix.
Right. Okay. And then U and V, they on the one hand they determine Y. Y is
A plus epsilon.
A plus epsilon.
A so Yij is Aij plus epsilon Ij.
And Aij is what you care about.
So Aij is Ui transpose Vj,
Okay.
and then epsilon is the noise.
Noise. And Dij is whether it's not Aij plus noise.
No.
It's whether it's revealed or not.
Or not. Okay, and across, for example, in previous model, Dij and Di prime j are I prime j prime are independent random variables. Here they may not be.
So one there is the noise, one is the randomness and the revelation, which is okay, both driven by you.
Yeah. Okay. All right. So it's 11:40. So maybe I'll have 10 or 12 more minutes. Okay. So.
Go to 12, as I said.
No.
I'll use my power as opposed to.
No, I won't abuse it. Okay. So let's do this. So again, sort of, this is the confounding problem. We all know what confounding is. If actually you can sort of, if you don't do randomized control trial, it can lead to bad answers. And I'm going to skip this. Okay. Let me do sort of the quick literature review before sort of I sort of just show the algorithm and results. Okay, so there's a very large literature, and I'm just doing sort of a highest level decomposition of them. There's a spectral optimization, and I would say nearest neighbor. And again, in spectral, one really nice simple algorithm is universal singular value thresholding, which says take the matrix, fill the missing values by something deterministic, say zeros or the row mean, column mean. Do singular value decomposition, remove the lower components, keep the key components, and that will be that. It's really nice. And then just normalize by fraction of entries observed. Is optimization based algorithm. One of the algorithm, for example, is soft impute, and for example, Rahul has a really nice way to implement it. So if you play with this, you will realize that there's really something nice happening there. This is empirical risk minimization view with appropriate regularization, and then there is a typical nearest neighbor like approach, and again comes from the collaborative filtering algorithm. And then finally, in the same category, I would put this synthetic controls method for panel data because it's trying to do something like that. Okay, and there's a nice scoreboard which says a sort of in Mnr setting, what is the minimal number of samples you need to have a consistent estimation. Okay, and I'm going to sort of skip this, but the point is there's a huge literature out there there's a lot of focus on Frobenius norm, but again, sort of there are few recent progresses about infinity norm. In particular, there's a nice work by Chen et al. that tries to actually obtain entry-wise Gaussian approximation under low-rank setup, which is kind of a mixture of convex, non-convex methods. Okay. All right. Let me sort of go to the Mnr setting. And again, so I pointed out some of these references earlier. There's a relative performance guarantees like regret-like guarantees that are there. And again, this is just one of them, the many results. There's a recent work by Bhattacharya and Chatterjee. Actually, literally, it came out last month. Talks about consistency estimation there. And then in the panel data setting, which is specific pattern, observation pattern, there's a lots of interesting results there. All right. So just to make the point of that Mnr is different from the typical thing, I'm going to sort of walk you through this simple example. And hopefully that will be all I really want to communicate. So it's an 80 by 80 matrix. Okay, it's rank 5 matrix. The way factors are generated are effectively by sampling each entries of the factors as per independent Gaussian and then just normalize them. Okay, and then based on that we generated the matrix. Then what I'm doing is I'm just plotting the histogram of entries of the matrix, true matrix A. Okay, so that's this one. Then we went ahead and sort of sampled entries at random as per the MCAR setup with some p, small p. Okay, and now what I'm showing you here is that sort of the histogram of observed entries. And again, I'm keeping the frequencies, so I'm not normalizing. But as you can see, shape is same. So if I normalize it, they'll look the same. Makes sense, right? I mean, I'm sampling the things from the underlying distribution. Of course, if samples are enough, I should match the thing. Now, from these dark blue thing, I run USVT on it, and this is what comes out as the histogram of my completed entries. As you can see, it's really shrinking. Okay, it's shrinking towards the global mean of all entries rather than per entry means. So it's definitely biasing a little too much. Okay, and again, notice the difference in the scales. Okay, this is what happens to soft impute. Pretty good, right? At least at this level. And this is what happens to the algorithm I'll present. Okay. So at least it doesn't lose performance as it should. Okay. Any questions about just what I'm presenting here? A super simple experiment. All I'm saying is that it's under missing completely random. Soft impute does really well as expected. So does the algorithm that I'll tell you in a second. And USVT, even though it's there's a really nice theoretical guarantee, actually it does not work well, at least as well as I would have expected. Okay. Now I'm going to do limited Mnr setting. And what limited Mnr setting is that again for each entry there's a PIJs are different, and they're function of actually this latent factor itself, which is a low rank function. And so this is how the pattern looks like, very much like how effectively a panel data like setup. Okay. And again, so that's a true histogram as before. This is the sampled one, and as you can see, it's now a little bit distorted. Okay, even if I scaled it up, it would scale it up differently. Okay. Now, while visually this might look like USVT has started doing well, don't be fooled, because look at that. Okay, it's actually really sort of now skewed. So it's doing worse. And now there's a clear bias induced in soft impute too. Okay. And this algorithm continues to do well. Now in this one, I could do the inverse propensity weighted version, and it would be terrible. I mean, I won't be able to sort of show you anything in the plot. So I'm not showing you that. So actually, interestingly enough, limited Mnrs, at least this setup, not doing correction for USVT is a good thing. Okay. All right. So now I'll go to the causal Mnr. Any questions so far? Okay. All right. So this is how the pattern is, and again, sort of some places are sort of deterministically zero, some places are not. The choice of this was done dependent on the all the latent factors. Okay, there's a simple deterministic function there, and so the samples look like this. Okay, so they are biased. This is what happened to USVT. Again, look at that; it's pretty high. Soft impute again sort of ends up doing now quite poorly. Lots of things are out. We are sort of thresholding it back because I know the range of the observations, and this is what our algorithm is doing. Okay, so it sort of continues to remain robust. All right, so that was in a nutshell the point of the talk. That despite the algorithm, of course, is agnostic of how the data is generated. It just looks at the observations and runs it. And I'll tell you in a second. It's super simple. It's not complicated at all. Okay? All right. So synthetic nearest neighbors. So it's nearest neighbors and synthetic control put together. That's all. And that's why the best name we could come up with is the synthetic nearest neighbor. Okay, so how does it so nearest neighbors, how does it work? Just to remind us through a caricature. I'll just take 5 more minutes. Okay, so I want to fill this entry where I'll look for rows that look similar to me, effectively in L2 norm, and then transport their values for this column by averaging them. This is the user version, and then there is, of course, the column version. And in an ideal world, you would find all the rows and columns that look similar to you, and then average over that submatrix of rows and columns that you have observed. Okay. Synthetic control, how does it work? Synthetic control is for very specific observation pattern of this type. There is all but one row has few missing columns. Okay, and so you want to fill this up. So how would you do that? You would say that let's look at data for which all columns have entries. These are my features and these are my labels. And I learn simple linear model. Okay, and then use this linear model to do the predictions. Nothing complicated. Of course, there is a regularization for linear model happen in the original method. The regularization happened by restricting W's to all component being non-negative and adding up to 1. So it's a convex that way. Okay. What we will use the version where we will simply do the PCR of it. That is, take the features, do the denoising, and then sort of it will be low rank matrix now, and then sort of use the low rank, then do ordinary least squares. Okay, so now I'm going to put all of these things together. So imagine that sort of the observation pattern looks like this. I want to estimate this entry. Okay, there are some observations in this row I know. There's some observation in this column I know, but I don't know this. So these are the columns of my interest, and these are the rows of my interest to begin with. Then among them, I'll go and look for, if I could, look for, so columns of interest, rows of interest. And then what I will do is I'll look for this, in this rectangle, look for observations that are fully observed. Let's call this S. Okay, so I've got a small rectangle where all entries are observed. Okay. And now I'll do effectively, now I've sort of thrown out everything, put this together, bring this together, and let's say this is the only entry that I want to observe, and I will treat it as a synthetic control problem or a robust synthetic control problem, and that's it. Okay. Now, of course, there are a few variations that are there. I will do a little bit of bootstrap-like things to actually get multiple predictions, and then do average to get central limit. But this, in a nutshell, is the method. Okay, so not complicated at all. Okay. Any questions? Okay. And of course, now to prove theorem, you need assumption. For assumption, one thing is you need sort of some rectangle existing there. So let's assume that I've got at least some rectangle that is parameterized by this existing, so that I can write down a clean statement on the next slide. Okay, so let's say k by k raised to 3 by 2 size rectangle, whatever that k parameter is. Maybe k is 1, maybe k is large. The noise are sub-Gaussian. As I said, is a balanced spectra, which is related to that condition that Fan et al. Called passivity, and then incoherence. And once you have that, the per entry error would scale like k to power 1/4 in denominator. So higher the size of pattern you have, smaller the error you will have, and scales with r raised to 3 by 2 in the rank. I think we believe it should be r, not r raised to 3 by 2, but that's what we get. Okay, and so that's sort of just under the assumption that you have a pattern like this, subject to all the other dependency constraint. But in a sense, it restricts some form of dependency, right? Because requiring of existence of such a rectangle for a given entry. Okay, and this is entry bias result. So it may be true that for some entry you might get some k, other entry you might get some other k. Okay. Just going back, one can ask question that for typical Mnr setting, where of course we applied the algorithm, would it work or not? Here is just a simple calculation would reveal that if you want, let's say, error to be, okay, I was trying to figure out where I should put 12. So if error want to be delta raised to 1, 12 raised to 1/2, maybe you need p to be scaling like that. So there's a non-trivial probability. This goes to 0, and still you will have ability to reconstruct it. There's a natural Gaussian approximation you can get, which is if k increases, then the normalized error would go to Gaussian with the variance induced by that linear weight that you learn from your square that you or rectangle that you used. Okay. Maybe in remaining 2 minutes, I'll skip some of the experimental results. There's a very detailed comparison we did with things, and again, the bottom line is that for limited Mnr, there are a bunch of things will do really well, like max norm and this one. But if you go to the general Mnr, this ends up doing better than at least the known algorithm, with and without all the correction. And for example, LR is linear regression, logistic regression put together with as a way to do IPW to correct loss function and all that. Okay. Same thing for panel data setting. I'll skip all of this. I just want to do sort of 2-minute discussion, and then I'll end. Okay, so so this is usually the DAG that you see in causal inference. So there's an outcome of your interest. There's some intervention. If the world is really nice, which is randomized experiment, you can decide which intervention to choose independently of the confounders that determine the context of the units that get treatment and so on. And that's why this dashed line. But in observational setting, the intervention that is applied actually might depend on this. Ignoring the distributional aspects, functionally, effectively, it says that y is some function of, as a causal mechanism, some function of intervention you assign and the context that you might have. Okay, and in the observational setting is some other function of your things. So if you want to, let's say, find out for a given intervention A, what would be the outcome over population, we'll say, take things at random from population, units, individuals, and assign intervention A, and then see what the outcome looks like, and that's a reasonable proxy of that. But if I want to go and to look at that specific individual, let's say David got intervention A, but I want to go back and ask, hey, what if David got intervention A prime? Then if I knew function f, and if I knew David's u, then maybe I can apply f of A prime comma u of David, right? And then figure out what his y would look like. That's counterfactual. The problem is I don't know David's u most of the case. At best, I know partially. That's what one would call the there's a nice assumption that goes selection on observables or selection on covariates in thing where you would know that sort of what those things are, but really in reality you don't know. Okay, and if you don't know that, how are you going to learn F? And to make matters worse, if A's are sampled in really bad way, as it was in that baby example that I skipped, then there is no way you can sort of learn these things, even you know everything else. So effectively what things like factorization of matrix completion style world say is that, well, you might have function of these two parameters, but maybe it decomposes nicely into product of few things. Let's say rank is 1. So then it's just f of a comma u is some alpha of a, beta of u. Maybe A is a discrete thing. That is, you got a vaccine, you got a sort of pill, you got that. So really, there's no featureization that I care about. So really, at that level, it's again a latent factor. This is also a latent factor. So maybe if I have a data that looks nice and high dimensional, then latent factors associated with rows or columns or individuals and interventions are helping me learn some of these things. And then now I can sort of do extrapolation. Okay, and again, sort of data might be sort of confounded as it was generated, but if the right patterns are revealed, then I will still be able to do that. And our hope was that this, at least this simple algorithm and simple setup I presented would be a step towards something like this. Okay, my hope is that many of you would go back and look at the model and say, well, this is extremely simple algorithm. I can do much better. And I hope that sort of some of you would do much better in weeks to come, months to come, maybe year to come. Okay, so that sort of model will remain, not the methods. All right, with that, let me stop.
Thank you very much. Let's open the floor for questions.
Yeah, Becca?
If you have multiple rectangles, do you repeat the algorithm and average, or do you just pick the best, somehow pick the best rectangle?
Repeat and average.
So the bound was for averaging over all of them.
Absolutely, yeah. Thanks.
I have one, maybe it's too detailed, and one of the slides you had, if the probability is 1 over m to the delta and the
Yeah.
delta, is this meaningful when delta is like bigger than 1 still? Because I'm not sure about this.
No. So yeah, so I meant this one. Yeah, so
Yeah.
here the thought was maybe delta is really small, closer to 0, rather than it's between 0 and 1.
Between 0 and 1.
Yeah.
Because if delta is bigger than 2, then you don't, with high probability, you're not observing anything, but
Yes.
yet you get something presumably non-trivial here, which is a little
Yeah,
strange.
which is useless. Yeah,
Okay.
absolutely. Thank you.
All right. Well, you feel free, I guess, to
Yes.
approach Devarat offline, maintaining the properties of
Distance.
and
And the math.
we'll see you next Friday. Thank you.
Okay. Thank you. Thanks, David.